Let's work through this geometry problem carefully, step by step. And I want you to pay attention to the main idea, because although the diagram looks complicated at first, the calculation becomes surprisingly clean once we recognize the structure. We have a large semicircle, and inside it we have two smaller semicircles. Let the diameter of the smaller semicircle on the left be P, and let the diameter of the smaller semicircle on the right be Q. These two diameters sit next to each other along the diameter of the large semicircle. So the diameter of the large semicircle is P plus Q. We are also given a perpendicular segment from the common point of the two smaller semicircles up to the arc of the large semicircle. And this segment measures 8 units. Our goal is to find the area of the shaded region. Now, instead of trying to calculate the shaded pieces separately, we are going to use a much smarter approach. Think about what the shaded region actually represents. It is the part inside the large semicircle that is left over after removing the two smaller semicircles. So, if we could turn all 3 semicircles into full circles, the shaded area would simply be 1/2 of the difference between the area of the large circle and the areas of the two smaller circles. The reason for the 1/2 is very important. Each shape in the original diagram is a semicircle, and a semicircle is exactly 1/2 of a full circle. So we can temporarily imagine the corresponding full circles, perform the area calculation there, and then take 1/2 at the end. Let's write that carefully. The shaded area equals 1/2 multiplied by the area of the large circle, minus the area of the first small circle, minus the area of the second small circle. Now remember the circle area formula when the diameter is given. Normally, the area of a circle is pi multiplied by radius squared. But if the diameter is d, then the radius is d divided by 2. Therefore, the area becomes pi multiplied by d squared divided by 4. That formula will make this problem much easier because all 3 diameters are already available. The diameter of the large circle is P plus Q. Therefore, the area of the large circle is pi multiplied by P plus Q whole squared divided by 4. The first smaller circle has diameter P, so its area is pi multiplied by P squared divided by 4. The second smaller circle has diameter Q, so its area is pi multiplied by Q squared divided by 4. So, our shaded area becomes 1/2 multiplied by the quantity pi multiplied by P plus Q whole squared divided by 4 minus pi multiplied by P squared divided by 4 minus pi multiplied by Q squared divided by 4. Now, let's simplify this carefully. Since every term contains pi divided by 4, we can factor that out. So the expression becomes 1/2 multiplied by pi divided by 4, multiplied by the quantity P plus Q whole squared minus P squared minus Q squared. Notice that the 1/2 is still outside. Now comes the key algebraic step. We need to expand P plus Q whole squared. Remember the identity, a plus b whole squared equals a squared plus 2, ab plus b squared. So in our case, p plus q whole squared equals p squared plus 2, pq plus q squared. Let's substitute that into our expression. The shaded area becomes 1/2 multiplied by pi divided by 4, multiplied by the quantity p squared, plus 2 pq plus q squared minus p squared minus q squared. Now look carefully at what happens. We have a positive p squared and a negative p squared, so those cancel. We also have a positive q squared and a negative q squared, so those cancel as well. That leaves only 2pq. Therefore, the shaded area becomes 1/2 multiplied by pi divided by 4 multiplied by 2pq. Now, pay attention to the simplification. We have a factor of 2 from the expression and a factor of 1/2 outside, so those two factors cancel each other. What remains is pi multiplied by pq divided by 4. So we have reached a very useful formula. The shaded area equals pi multiplied by pq divided by 4. And notice something interesting here. We do not actually need to find p separately, and we do not need to find q separately. We only need the product p multiplied by q. That is the clever part of the problem. So now our entire task is to determine the value of pq. To do that, we use the intersecting chords theorem. Before applying it, let's understand why it works here. If two chords of a circle intersect inside the circle, the product of the two segments of one chord equals the product of the two segments of the other chord. In other words, if one chord is divided into lengths m and n, and the other chord is divided into lengths r and s, then m multiplied by n equals r multiplied by s. Now look at our large circle. The horizontal diameter is one chord, and the common point of the two smaller semicircles divides this diameter into two pieces. Those two pieces have lengths p and q. So one product is simply p multiplied by q. Next, consider the perpendicular chord through that same point. We are told that the distance from the diameter up to the large semicircle is 8 units. Because the full circle is symmetric about its diameter, if we imagine extending that perpendicular segment downward through the diameter to the corresponding point on the opposite side of the full circle, the lower portion is also 8 units. Therefore, the perpendicular chord is divided into two segments of 8 units each. This gives us everything we need for the intersecting chords theorem. The product of the two horizontal segments equals the product of the two vertical segments. So p multiplied by q equals 8 multiplied by 8. Now calculate that product. 8 multiplied by 8 equals 64. Therefore, PQ equals 64. This is exactly the value we were looking for. Now let's go back to the formula we obtained earlier. We found that the shaded area equals pi multiplied by PQ divided by 4. We now know that PQ equals 64, so we substitute 64 for PQ. That gives us shaded area equals pi multiplied by 64 divided by 4. 64 divided by 4 is 16. Therefore, the shaded area equals 16 pi, and that is the exact answer. So the area of the shaded region is 16 pi square units. Notice how beautifully the problem comes together. We never needed to calculate P and Q individually. We first transformed the semicircle area problem into a full circle area expression. then expanded p plus q whole squared, canceled the p squared and q squared terms, and reduced the entire area calculation to pi times pq divided by 4. Then the intersecting chords theorem gave us pq immediately as 64, and one final substitution gave us 16 pi square units. This is a great example of why we should not rush into calculating individual lengths when a geometry problem gives us a more useful relationship between them. The important quantity here was not p by itself or q by itself, but their product. If you followed that key idea, then you have essentially unlocked the whole problem. If you enjoyed this solution and found the shortcut useful, take a moment to like the video. And if you have another geometry puzzle you would like to see solved, leave it in the comments. And if you want more problems like this, consider subscribing to the channel. But remember the main result from today. Once we establish that the shaded area equals pi times pq divided by 4, and the intersecting chords theorem tells us that pq equals 64, the final answer follows immediately. The area of the shaded region is 16 pi square units.